All right, let's give this one a go for the last problem solving here. Try this one out and come check your answer. We're launching a golf ball, some unknown distance this time, but we know the incline angle of that hill. We know the launch angle from that hill upward, and we know the initial launch velocity. So we've definitely still got a case where we have acceleration that's constant in the y because we have gravity, and no acceleration in the x. So we can use our good old equations, split them into x and y, and they want us to find the distance d, this uh, this diagonal distance where it's going to land. So if we call this our x and y system, let's make our two equations. There's only one x, and then we'll pick one for the y. And I'm thinking let's use the one that involves distances, right? Initial and final position, and initial velocity somehow, right? For the x, it's easy because there's only one equation. So we'll have the initial position of 0 and the final position, xb, is going to be d cosine of 10 if we split this into sine and cosine for the horizontal and vertical distances there. So there's our initial at a is 0. And our initial launch angle, we need to add this 10 and this 45 to get 55. We've got 80 cosine 55 times the time, and they said time AB. All right, that's the time for it to get from there to there. So we've got two unknowns there. We need another equation that has those same two unknowns. And so we've got in the y equations, well, if we use the one that has the initial and final positions in it, this guy, right, we will also know the initial velocity, right? We could have 80 sine 55, and then we've got gravity. This one will end up having d and t as the unknowns once more. So that's a good one to use. So our final position, yb, would just be d sine of 10 this time. So there's yb starting from ground zero here. And our initial launch we said was 80 feet per second times the sine of 55 this time for the vertical component times t. So what I've done here is I'm already plugging in this from our x equation in for t. So you could do it one way or the other, but it's going to be a lot easier to solve this x equation for t in terms of d and plug that in for t rather than the other way around. If we were to plug in d into this equation in terms of t, then it would just get a little bit ugly. We'd have to solve a quadratic. It's still going to be a quadratic either way. So probably either way. But since we're looking for d, might as well plug it in terms of d and solve it immediately for d rather than solving for t and then plugging back in and solving for d. So that's what we're doing here, plugging in this value, this solved equation for t in for t in the y equation, minus, and this is really plus 1/2 at squared, but we're saying minus because we want this gravity to be going downward acceleration. So minus 1/2 32.2 is gravity times t again, squared. And make sure both of those terms get squared, right? So we end up with this squared and the d squared. You can simplify it, but if you would rather just plug that guy into your calculator's solver function, that should be able to pop out your variable there. And it should come out somewhere in the realm of 166 feet, plus or minus a little for rounding. But that would be that diagonal distance d that it travels. So that is it for this problem. And for projectile motion, really it might get a little more complex than that if we have to like solve for the angle, but it's all just algebra from there, right? The trick is just setting up your singular x equation. It's always going to be the same equation. You just plug in what variables you have and leave out the ones you don't have, and then pick one that matches what you're given and what you're looking for out of your y equations. And with the combo of those two equations, we can do a lot of powerful stuff using our constant acceleration equations in avoid the hassle of needing to reintegrate those equations or anything like that.